So welcome back after Puja holidays, and in Bengal we say Shubho Bijaya, which means happy Puja greetings. So we are going to start our module of the course, you can say. The first module was on probability, second module was on filtering, basically based on input output models. And so now we are coming to the third model, which is state estimation, and basically we will study for the large part of this module the Kalman filter. So today we will recapitulate and try to motivate the Kalman filter as to why it is needed and in what circumstances it is needed, by starting right from the basics. That is, we'll take a look at the problem and see there are various kinds of solutions proposed for various kinds of situations. So we'll start from a very simple situation where most of the things are known and something is unknown, and we will try to estimate the state in that situation. Estimation is always applicable where there is some uncertainty about something. So we will gradually see that as we remove assumptions of certainty about many things, situation becomes more and more complex, and then more and more complex algorithms are needed, right. So we'll go that way, and we'll first, just for the sake of completeness, this is very familiar to you all as to what is a state. That is, I want to distinguish between the output and the state, right. So as we all know that the state is the set of signals of the system that fully captures the effect of past inputs. Why this is so important? Because of the fact that we always, when we try to characterize systems, we always look for finite descriptions, something which can be described using a finite number of quantities. If we have to describe something using a very large number of quantities, then it is very inconvenient, right. Now there is a problem of dynamic systems. The basic characteristic of dynamic systems, by which dynamic systems are different from static systems, is that they have memory, right. So they actually remember in some fashion, they will remember the effect of all past inputs. So the behavior, that is the future behavior of the system, cannot be described just by giving the future inputs. Ideally speaking, theoretically speaking, you need along with that all the past inputs, right from the state when the system was first constructed at time is equal to probably minus infinity or something. Now this is a very, very inconvenient situation. If you want to, how do you deal with it? You need an infinite number of samples of inputs to be able to compute any, let us say the output at any instant. So therefore this property has to be circumvented. So people proposed models by which this property can be circumvented, and the concept of state came in. So now we say that if you know the states, then they hold all the information about the past. So you only need to know the state at a given point of time and the inputs from there on. So the past is encoded into a finite number of quantities. That is the biggest advantage, right. So now you have x1, x2, x3, x4, xn, 5 quantities which will hold the effect of all the past inputs, right. So you can say that the future Now the future state can be now expressed very succinctly in terms of the past state and this input. So it is a very finite description, though the system has infinite memory, but that memory has been encoded into a finite number of quantities. That is the beauty of it. And well, we are obviously interested in outputs. In fact, we are not interested in outputs. We call those signals as outputs which we are specifically interested in and which we might measure. So it is by definition that the outputs are measured. I mean, those signals are called outputs which are measured generally and which are of interest. For example, if you want to control some specific quantity in a process, we would like to call that as an output. While there may be many others which also will affect that, but we will not call them as output because they are not of primary interest to us, right. So, and it so happens that the output in which we are interested and which we measure are actually related by the state and the input. So this is the basic advantage of the state space model, as we know, with which we are all familiar, that number one, that the past can be encoded into a finite number of quantities, which is very easy to handle. If we have a finite dimensional system, we could also have infinite dimensional systems where even if we want to construct a state space model, we will require an infinite number of states. We are not talking about such systems. We are talking of systems in which the state vector is a finite dimensional vector. And so outputs are measured, but all states may not be measured, right. So there may be some other quantities which also affect the dynamics of the system, which will also affect the output, but they may not be measured. Now this is what actually makes the problem of estimation non-trivial. If we had measured all states, then we have no problem of estimation, I mean in most cases, but we have a non-trivial problem here because we are interested in calculating some of those states for some purpose even if they are not measured. That is what brings in estimation, right. So then we have this question as to why we need state estimation. Basically because of two facts. Firstly, that states may not be measured and we may still like to have them. So why do we like to have them? We may like to have them for various purposes. For example, typically, I mean this is an example with which in which I am interested, that if you want to, let us say if you want to construct a controls mechanism for, let us say, a rocket or let us say a missile which is supposed to hit, let us say, another missile or maybe an aircraft. So now the question is that this missile will have a controller, of course, and naturally it has to be given not only the controller. You see, in our code somehow we focus too much attention on the controls part. That is, we are always concerned about the control, and we never bother as to this R reference signal that usually comes in a control. Where does it come from? We do not spend much time on that, but it so happens that in aerospace control that is extremely important. In other words, you must tell the missile as to where to go, which direction to go. Then if you can tell the missile that, then the missile's controller's job is to obey that faithfully. You see, the job of any controller is to obey its command faithfully in the face of disturbance. So it essentially needs to have two properties. One is that it must follow reference faithfully. Secondly is that it must reject all disturbances. This is the desired property of all controllers. But there is this non-trivial problem of trying to compute the reference itself. That is, which direction should it go? After all, one missile is coming from here. So which direction should it go so that at some point they should meet, right? So that comes from what is known as guidance. Now obviously you can understand that if you want to hit something which is moving, then you need to know all its motion parameters. In other words, you will need to know its present position, you will need to know its velocity. If it's an accelerating target, then you need to know its acceleration. Otherwise, how do you hit it? You can't hit it. So, but it so happens that the kinds of sensors that are put on these vehicles basically sense position. So there is this non-trivial problem of trying to estimate velocity and acceleration given the position, which is not measured, right. So that invariably calls for having a Kalman filter, because you need to know the position, velocity and acceleration of the target, right. Similarly, there is a good amount of application in process control, right. In a process control, let us say if you want to control a distillation column. Now a distillation column has 30, 40, 50, 60 variables, all of which are actually coupled. They actually affect both the bottom product quality as well as the top product quality, and there are only a few, let us say typical distillation column control will have 5-6 sensors. So but for effective control, you need to be able to estimate other variables, because otherwise actually what happens, typically what happens, I mean the problem in process control is that because of the large nature of the process and because of the slow and accumulative nature of the process, what happens is that by the time you find that a problem has actually reflected itself in the output, the system has a lot of storage capacity. So the input that you are giving now does not affect the output immediately. So if you base your control only on the input, only by sensing the output, then what happens is that by the time you have seen the output, you have done lot of wrong things. So all those are actually stored, and you cannot, I mean even if you change the input now, you cannot correct the output now. Even if you change the input now, that effect will come later. So in such situation, there is a lot of requirement for sensing signals which are not measured. I mean these are very, I mean some typical examples, but there are many other examples. There are examples in motor control. For example, nowadays you have brushless DC motors are, I mean very common. They have become very important drive machines. Now one of the major difficulties of having a brushless DC motor is that you need to sense its position. I mean if you could do away with that position sensor, then it will be good. So I mean a lot of people actually put state estimators by which you can actually estimate the position based on the current measurements. I mean typically current is the easiest thing to measure. So there you can have an estimator. I mean similarly you can have lots of other examples where, I mean measurement of state, I mean rather estimation of state based on measurements is required for effective control. So I mean that is why state estimators are very important. For example, typically I mean this distillation column control problem is essentially a composition control problem. That you want to produce from the crude, you want to produce petrol of a certain quality. So if you want to produce petrol of a certain quality, it has a certain composition, only then it will have certain parameters like octane numbers, right. So essentially it is a composition control problem. So for such cases you need to have state estimators. There are, as I said, that there are various kinds of state estimation problems, and even I mean they differ on a number of cases. I just have mentioned 3 classes. For example, initially I mean the simplest state estimation problems are known as the state observation problems. Okay, what is the situation there? First of all, you have a known model, generally completely assumed to be known. Okay, it could be linear, it could be non-linear. We are going to concern ourselves mainly with linear, and I mean that is what we have or we are going to study in standard linear system theory courses. Okay, so you have the model known. Now the model, what is the model? The model is the simplest model, that is xk plus 1 equal to axk plus buk kind of model, or x dot equal to ax plus bu. Now in that, second assumption is that the input is known. So we are assuming that the total input vector u is known. In general, a system has two kinds of inputs. One kind of input is called the control input. These things are known, which is actually applied. The other kinds of inputs are called disturbance inputs, which are not applied, which are actually applied by the environment. So you in general have no control over them, and often they are unmeasurable. So in this case, for this state observation problem, we are not considering disturbance input in its simplest form. Okay, so all inputs are assumed known. What is unknown then? What is unknown is the initial state. So essentially the problem of estimation in the state observer problem is basically a problem of whether you can estimate, given a set of input output data, whether you can estimate what was the state before that. That is essentially the problem, okay, which actually leads to observability, as we will see. So, similarly, many practical things are not considered. For example, no measurement error. We will actually have measurement error, but typical treatment will not consider measurement error. Similarly, now since we have so many things, the problem that is considered is that whether we can asymptotically, that is with time, whether we can estimate the actual state, the exact value of the state. So the problem that we attempt to solve tries to get the actual value of the state with the error going to 0. This is what is attempted, because the situation is so nice. We know all the inputs, we have no noise in the measurement, we know the model fully, only the initial state is not known, right. So now clearly this situation is not realistic, right. So then we put the next set of problems, that is, okay, we now assume that let there be some noise in the measurement, and we also assume that let there be some uncertainty in the inputs, that is, some input may be known, but then there may be some other inputs which are unknown. So even if we consider them as unknown, let us at least assume that now one common way of characterizing unknown and uncertain things is to have a probability distribution, having a probabilistic description. So here in this problem, now we increase the complexity a little bit to make it more realistic. So we say that input is not exactly known, but the statistical properties of the input will be known. That is, it may have a mean, it may have some variance, we will assume those things. So we are now reducing our assumption of noise, our assumption of knowledge. Model is still known. Properties of initial state and measurement error, we now assume that there may be measurement error, but we assume their properties, what could be their variance, how much measurement error. And we also assume some properties of the initial state, that is, what could be our initial state, by how much can be our initial state guess known. So once we introduce these uncertainties, obviously we can never hope for computing the state exactly, because there is noise. So our estimates are always going to be erroneous. So therefore it is not meaningful to try to solve a problem where the estimation error will go to 0, it cannot go to 0. So therefore now we try for a minimum mean square error estimate, that okay, error is going to stay there, but can I make an estimator which is going to make my error power minimum. So now that is the problem which is attempted. Now once you have this, now you can have various other variants. For example, you can have a nonlinear version of the observer, which is much more complicated, because nonlinear dynamics is much more complicated. So same case, except for the fact that the known model is nonlinear. Similarly, you could construct unknown input observers, that is, whether it is possible that the effects of some of the inputs at least can be totally decoupled from the state. That is, even if I don't know them at all, by some way can I produce an estimate which will not depend on these inputs, right. So, we sometimes we make unknown input observer, sometimes we make we try to estimate the input separately because they are unknown, but we this is another class of estimator where a large I mean a significant input which is not probabilistically described is assumed to exist. Okay. Then there are extended versions of the Kalman filter mainly to take care of nonlinear cases, and there are also adaptive versions of it when the system tends to change from one type to another. So, whether we can have state estimators of systems which are varying. So, these are somewhat advanced problems. So, in the coming few lectures we will basically be concerned with this class of estimators, but today we will take a look at these just to kind of warm up. So, we will try to see what are the results on the simplest problem of state estimation. Okay. And these results I think you will also come across in your control theory class, these I mean observers and I mean observer based controllers, etc. So, we will not derive results, but we will see the basic principles against these results today.
So, in the state estimation the states are known, the initial states, the properties of initial states known means the initial states are known.
No, that properties of initial state known means that some initial state error variance may be known, right. Exactly initial state is not known. If exactly the initial state is known and if all inputs are known, then you can simulate it, right. If exactly initial state is not assumed to be known,
what is known?
Yes.
But in the state observer no property is also known.
State observer no property is known because in the state observer generally we try to design the observer in such a manner, as we will see, that as long as that error is finite, eventually it will come to 0. That is how we want to design it. So, the question is, so the first question, that is the first concept which is generally introduced, is that when is this theoretically possible, that is now we are considering this particular case, that is we have a standard model xk plus 1 equal to axk plus buk. You can have so the model is xk plus 1, we are considering discrete because that is simpler. Continuous creates many problems basically because of the derivative operator, especially if you have a statistical signal, defining its derivative is not simple. So, we are avoiding all that. So, this is our model, and you can have either yk plus 1 rather yk is equal to cxk, or you can have yk equal to cxk plus duk. It makes no difference because uk is known. So, you can always construct some other y dash k equal to yk minus duk. So, even then the left hand side will be known. So, we will generally assume that this is our model. In this ABC is known, u is known. We want to estimate x, but initial x0 is not known. Okay. So, the question is when can we even hope to solve this problem? So, that is given by what is known as the condition of observability. So, a system is said to be observable if we can uniquely determine the vector xk at time k given the input and the output sequences ui and yi for all I greater than k. That is, suppose the system started from k. Now, if you are given all the future inputs and outputs, can you using them can you compute what was xk? It is a kind of an initial state problem, right. So, if that is possible, then the system is said to be observable, right, whether you can solve out the state from which it started. I mean actually there are, if you see books you will find there are many definitions of observability. They can be shown to be mathematically equivalent. This is probably the one which is the most popular, but there are others, many others. So, note that I mean obviously this is, we will assume that this is with respect to a standard ABC or even ABCD. I have cut this D, but you could put this D as well, does not matter. So, we will assume that to the standard ABC model of the linear system in discrete time. So, we will treat this problem there. And so the basic question is basic question of observability is that if you are given uk, yk, uk plus 1, yk plus 1 etc., whether you can solve out xk. It is a question of solving out from a set of linear equations. So, basically it boils down to the solvability of a set of equations. And what are those equations? These are the equations. Why these are the equations? That is very simple, because you cannot see, you want to find out xk. Xk has how many components? Xk has n components. Let us say it is an nth order system. So, if you want to solve out n components, you need how many equations? You need n equations. You need not only n equations, you need n linearly independent equations. So the first thing that we have to do is that we have to set up those equations and then solve it, right. So basically, and these equations must be set up with u and y, because they are what we know. So then so you can always write that yk is equal to c xk. This is the first equation. Second equation is, now what is yk plus 1? It is equal to c xk plus 1. What is xk plus 1? That is equal to c into axk plus buk. That is equal to caxk plus cbuk. So this gives you the second equation. See, all equations must involve x. Similarly, you can have yk plus 2. Go on doing it, then if you do it, you will get c s square xk plus c a b uk plus c b uk plus 1. This gives you a third equation, right. Now there is something. This is not a third equation. I mean, ideally speaking, if you have multi-input, multi-output system, then this is p equations, this is p equations, this is p equations. Each of them are actually, because y could be a p dimensional vector, right. So it could be, if it is a single input, single output, then one equation you need n. But if all you need are n independent equations. So how many of these equations you will consider depends on, if you go on doing it, how many of them you need to first get a set n. For example, suppose p is 2, n is 4, it could very well happen. Then maybe from the first 2 you will get 2 linearly independent one, from the second one you will get 1. So that means that from the second set you will get 2 equations, but one of them will be linearly dependent on either these and the third one. So that is not an independent equation. So you have to find out how many independent equations. By doing this, you have to find out n independent equations. They should not be linearly dependent, right. So now the question is that how many of them you actually need to consider. Whether you should take p is equal to 1, whether this will clearly not do, because generally p is less than n. So you have to have another one, but whether by considering yk plus 1 only you will be able to find, or whether you need to go for yk plus 2, how do you determine that? So then there is this, so it can be shown by a theorem which is called the Cayley-Hamilton theorem, which says that you need to consider maximum up to ca to the power n minus 1. That is, you need to consider only these, because if you take more, then by taking more of them you cannot generate another linearly independent equations, or whatever linearly independent equations you can generate, you can hope to generate, you can generate only with among these. If you take ca to the power n, ca to the power n plus 1, no new linearly independent equation will be generated. That follows by a theorem which is known as the Cayley-Hamilton theorem, which is, I don't know, you must have heard about it. So if there are n independent equations, they will definitely occur among up to this. If there are not, then bad luck, you cannot solve for x. Okay. So, now it turns out that if you, so this matrix is called the observability matrix. So, when we say that celebrated condition of observability that this matrix should have rank n, what we basically mean is that there should be, you should be able to set up n linearly independent equations to be able to solve for the n linearly independent unknowns. That is the meaning. Okay. So it should have full rank. Why full rank? Because what is this matrix? This matrix is np into n. There are np number of columns, each one of them is p. So there are n of them. So there are np number of rows and there are n number of columns. C has n number of columns, correct? So obviously an np into n matrix cannot have rank more than n. Rank is minimum number, minimum of, maximum possible rank is minimum of row and column number. So that is why since this matrix should have rank n, so it is called full rank. It is actually a non-square matrix. If this is a single input single output system, then this matrix happen to be n by n because p is 1, in which case full rank means invertible or non-singular. So in the CISO case, this matrix is required to be non-singular. So obviously you can know that here this is known. We have assumed that we have exact values of output without any measurement error. This is known. We have assumed that we have exact values of input without any error. So then that means you can bring it to the left hand side, and then the left hand side will be known. So if you bring it to the left hand side is known, and here you have a matrix into x. So to get x, what you have to do? You have to invert it. So, but you cannot invert it because it is a square, because it is a non-square matrix. So then you have to do pseudo inverse, that is you have to do theta transpose theta inverse. Do you understand what I am saying? If you have y is equal to ax and then x is non-square, then how do you solve for x? You say A transpose y is equal to A transpose ax, and then you say A transpose A inverse A transpose y is equal to x. So you can do that. Now who says that A transpose A inverse will exist? That is actually established by this. If it has n rows, it will happen that this will be invertible. So this is the way you essentially can solve for x. So if it is observable, it simply means that these equations can be uniquely solved for x. All right. But that is not the way we want to do it. We want to do it in a different way. We will see that. So now, so at this point, let us also mention that though I have talked about observability, if you see a slightly advanced text, you will find many other abilities. You will find, for example, there is controllability, there is reachability, there is stabilizability, there is, just like there are these three for control, there is a dual on the estimation side. So you have observability, you have constructibility, and you have detectability. Okay, they are actually one are actually counterparts of others. So anyway, we are not too much concerned about this particular problem. I am just trying to impress that this state estimation problem, just basically trying to get its character. Our main procedure of interest is under stochastic conditions, that is Kalman filtering. So we will not go into this, but just want to mention, I always like to mention what is not mentioned in the class. So these also exist, basic variants of the same thing. Interestingly, remember that observability depends on choice of measurement. You see, many times these things are generally not treated, in the sense that if you are, let us say when you are planning a system, probably system will be given. I mean, a distillation column is a distillation column. You cannot do much about it. But you probably can have a choice as to where you are going to put the sensor, right? So choice of measurand is important. For example, you can easily show that choice of measurand can make a system observable or unobservable. Okay, a very simple example is that if you measure position, you can extract velocity from it, but if you extract velocity, you can never extract position from it because you won't know the initial position, right. So sensing velocity, you can never hope to get position. So that state can never be observed. For example, suppose you set up a model in which position and velocity are the two state variables. Then if you measure velocity, then this system is unobservable because you can never get position from it. But if you measure position, if you measure that state variable, if your y is 1 0 rather than 0 1, C matrix, then you will find that your system is observable because from position you can get velocity. So we must remember that the choice of which variable you are going to measure can affect whether you can estimate the state or not, right. So basically observability is more of a theoretical interest in the sense that it tells you, it's important because it tells you that structurally whether the system is such that, you know, when a system is not observable, what happens? What happens is that because of the peculiarities of the A and C matrix, some of the state variables are not reflected on the output. Structurally they are not reflected. If you multiply C into X, it will tend to become cancelled, right. So it basically gives you a kind of a structural information more than a, you know, I mean in a very idealistic case, that is what usually it is. So let us see that what are we going to do with this observability thing. We are going to construct an observer. Okay. So what is an observer? It is an algorithm that produces an estimate of state called x hat k. I am differentiating it from xk. Xk is the true quantity, x hat is the estimate, and it does it, you know, recursively. As you get inputs and outputs, it continuously gives you a new estimate. Okay. That is an observer. So again, assume is that model is known, x0 is unknown. So even if x0 is unknown, we want to set up a system such that eventually, even with unknown x0, my estimate of xk will come close to the true one. That is what I want to do. So what do we do? Obviously we have to do this part of the thing. So this is the basic equation which says how am I going to update my estimate. So I had an old estimate. From that old estimate I want to compute a new estimate at a new time instant. So obviously since the true state goes through axk plus buk, obviously I have to do that with my new estimate also, with my old estimate also, only then. So this is a kind of, you know, open loop simulation. So I had an old estimate, I am assuming as if it is true, and normal system dynamics I am doing a one step ahead simulation of that. But then just that will not do. Why it will not do? Because if I keep on doing this, then my initial condition error will not die. I want to make my initial condition error die. So to do that, I must always correct. See, every time I am producing an estimate, I want to check how good it is. So how do I check that? I don't have a measurement. So I can't check that directly, but I have y. So I can at least check whether Cx came close to y. I cannot check, I don't have a measurement for x. So I cannot check whether my x hat was good. But I can at least check whether my Cx hat was good with respect to my y. So this is the feedback that I am giving. That every time I am getting an error, I am trying to correct my estimate, not only with an open loop simulation, but with a correction term, right. So that is how I am updating my estimate. So this is my observer, and the crux of the problem is how do you choose this. In linear state estimation, this is the crux of the problem. Most estimators will have the same structure. Even the Kalman filter has this structure. But all the trick is how do you choose this k, right. Right now in the observer case we will choose k as a constant k. Now how do we choose this k? So let us see that what is my objective of choosing k? My objective of choosing k is that my estimation error dies down. That is my objective. So now let us define my estimation error. This is x tilde k plus 1 is my estimation error, which is x k plus 1 minus x hat k plus 1. So how does that evolve? So if you just put x k plus 1 equal to ax k plus bu k and then rearrange, you will get this term. So you see that this becomes a homogeneous equation. Bu term will get cancelled. Why? Okay. So xk plus 1. First of all, note that this is cxk. So then this term is actually kc into xk minus x hat k. So it is kc into x tilde k, this term. And if you do xk plus 1 minus this is equal to axk minus buk. So if you subtract, then what will happen? It will be a into x minus x hat, b will get cut. So it will be a minus kc. That is how. This is very standard. I don't think I need to elaborate this. So now the question is, this was your error of estimation in the kth step, and this is the error in the k plus 1th step. So it shows the one step evolution of the error. Now why should this error die? This error will die if this matrix is stable, in the sense that it has eigenvalues on the inside the unit circle, then it will contract, correct. And so the whole problem of choosing k is such that you choose k such that this has eigenvalues inside the unit circle, and you can theoretically prove that if the system is observable, then you can choose k always to make this to be have its eigenvalues, that is arbitrary pole placement is possible. That is the good result. So if the system is observable, then you can always place the poles or always make it stable. Now the question is, so make it stable means what? Make it stable means that error will eventually die. Now eventually means how long? We want the error to quickly die. So if you want to make this error quickly go to 0, what we should do? This should have poles in the deep in the left half plane. If it has poles close to the imaginary axis, even if in the left half plane, then this is not going to die fast. It is going to die slowly, right? Right or not? Obviously, because all its poles will I mean, if you find a time domain solution of this, you will get e to the power minus lambda 1 t, e to the power minus lambda 2 t, etc. But those lambda 1, lambda 2 are the eigenvalues. So if lambda 1, lambda 2 have high values, e to the power minus lambda 1 t will quickly fall to 0, correct. Now the question is, so then why don't you make it infinity, make k terribly high? After all, this is all in your computer. This is not like control that you have to apply actual physical signals. In the case of control, you cannot make this very high. Why? Because if you make this very high, then your control inputs become very high, and you cannot apply such control inputs to the plant because you will have limitations. You will have actuated saturation. You cannot apply suddenly, you cannot apply 20,000 Newton meter torque. So even if you compute that control, the plant is not going to get that, right. There is a physical limitation. Now here there is no such thing. You are doing it all in the computer. So have a 32-bit word and make k high. What stops this? What will stop you actually is that what we have not considered. We have not considered any measurement noise. But if you have measurement noise and if you make this k high, then all that measurement noise will actually come in your estimates. That is, theoretically you will get a very good estimate if you make k high. I mean, if you make k such that the poles are deep in the left half plane. This is all theoretical, but actually what will happen is that there will be some sensor noise, and those sensor noises are here, right. So if you have some noise here, you can imagine what will happen if you make k high. Poles will go to the deep left half plane if you have high values of k, right. So that is why practically you cannot make k too high. So it is always an optimization of how close you want to I mean achieve your estimation error and how much measurement noise you want to pass, right. So that is the practicality of observer design. Now the last concept that we want to consider is that why should we, here we were estimating the whole state. So we have an observer which is an n dimensional system. So we have to update n equations, right. This equation has to be computed in real time. So why should we update n equations? We already have p of them in my hand. We have p measurements. So why don't I update only n minus p of them? P of them I always have, I mean I already have as output. So why I should again update them? So there may be a situation in which you may not like to update, may not like to estimate the full state. Rather you would like to estimate an n minus p dimensional quantity which is a smaller dimensional quantity, and then take the output and these quantities to estimate the full state. So only estimate n minus p of them. P of them you already have as measurement. So make them and then give some linear transformation or something to make the exact vector. Then at every time instant you have to update only an n minus p dimensional equation. So it is much simpler. It will take less computation time, right. So when we do that, we have what is known as a reduced order observer. So what do we, actually this statement is not exactly correct in the sense that observer only those states for which there are no outputs. I mean this sentence I feel I wrote it, then I had misgivings about it, that I mean there it's not that you have I mean one output corresponding to each state, this output is for state number 2, nothing like that. But the basic idea is that if you have p outputs, then estimate n minus p of them and then try to make up the state from that without having an observer. So I mean how do you do that? So now define a new variable called z, which is t into x, where where this z is an n minus p dimensional vector. So smaller dimensional vector, which means that this is an n minus p into n dimensional matrix. So basically you are considering linear combinations of x, of the elements of x, and you are considering n minus p such linear combinations. That is the whole idea. So now this is a quantity. Now try to estimate z. Now the question is that what is the beauty of this z? Beauty of this z is that you choose now y and z. If you make this vector, it will be ctx, because y is equal to cx, and you have chosen z such that z is equal to tx. Now if you choose t in such a manner that this matrix is invertible, then you could write x is equal to ct inverse yz. You could get x. So you see, if you can estimate this lower dimensional thing, this you already have, you do not have to do anything for that. So you estimate this lower dimensional thing and then from there you can get x. So the estimator only needs to have n minus p dimensions. So now the problem is how to construct an estimator for z. Alright. So how do you do that? That's relatively simple. We will just finish it now. So let us construct an, after all, if you want to use an estimator, what all you can use? You can use u values, you can use y values, and you can use the past estimate values. Other than that you do not have anything. So I am just assuming that and we are assuming a linear structure of the estimator. So I am just assuming that let z hat k plus 1 be some d into z hat k plus some e some g. I do not know, I have just made the most general possible estimator structure. Then I will find that what are the properties of d and g required. But this is a very general form. After all, you could not use anything else, correct. So now let us see what happens to error. So if so now my objective is to estimate this. So this is the error. So now how does this error propagate? Just like previous time I am doing. So now if you same thing you write z minus z hat k plus 1, like that you write. So you will get e k plus 1 is equal to d into e k plus these terms. This is just algebra. I mean you just put zk is equal to this is simple, just simple algebra. Now the question is that this is your, you see that this is the homogeneous dynamics and these two are there, these are like inputs. So if you can make these 0, then it will again be in that form. So first of all you choose, so now it is basically a design problem. So you choose T, D, what are the things that you choose when you design this observer? You first choose this T, then corresponding to that T you choose D, E and G, these are your matrices that you have to choose, then you get your observer. So you choose these such that TA is equal to DT plus EC, that will make this term 0, and put G is equal to TB, that will make this term 0, and also choose in such a manner that D is stable, then you will get this term will become 0, this term will become 0, and you will only be left with D, and then you choose D is stable, that is all. So then you get this Ek tends to 0. So this is the problem. Now how do you do it? This is I mean you have various kinds of algorithms by which you can actually make a choice. That those algorithms I am not discussing, but this is the essential principle of a reduced order observer. So we are going to end this. This is the concluding slide. So see that now so this is our observer theory. There is a significantly very interesting theory which says that if you use these observer estimates in control, then what happens? That is another story. It has very interesting results on that, especially in the context of robustness. But anyway, we are not going to that. So now our final remarks will be that theory is nice, but not really applicable in practice because of the fact that input may not always be known. Firstly, there may be non-idealness in the actuator. Secondly, there may be disturbance inputs. For example, on an aircraft there may be wind gusts which are not measurable. Similarly, output will always be corrupted with noise. I mean, if you are, for example, if you are using a radar for target tracking, there are n number of sources of noise in a radar, okay, various kinds. So output may be corrupted by noise. So therefore these assumptions that we made are rather unrealistic and cannot be actually used. And because this is not the case, so it is also unrealistic to actually try to match the state exactly. So we can never hope to make the error go to 0. So that is not the problem that should be formulated. So rather we should formulate an MMSE problem which will give me minimum mean square error. Error will persist, but its amplitude will be low, and now since we may not know it, I mean if we assume nothing is known, then we will never get any solution. So we will always have to say that something is known, something is unknown, which is the practical case. So the known part we will generally use, we generally express in the term BUK. That will like previous times we will still assume that is the known part, but we will assume that there is something more on that, and for that we will assume a probabilistic description, because if we have no description then we cannot produce any result again. So therefore we will use a probabilistic characterization of the unknown inputs and outputs, and as we shall see in the next class, that will lead us to the Kalman filter. Okay, so that is all today. Thank you very much.